Hello. Now we are going to consider type 2 error. Type 1 error is to reject a true null hypothesis, but type 2 error is not rejecting a wrong null hypothesis. So the truth is that the null hypothesis is wrong. So you had to reject it, but you could not detect the difference. So now we still have the same critical values. We are applying the same critical values to different drugs to see if they are correctly containing the correct amount. So the critical values are given, and of course the hypotheses are the same. Now we are going to calculate the probability of not rejecting the null hypothesis when mu is not equal to 0. When mu is not equal to 0. But the problem here is this assumption does not work well because we only say mu is different from 100. Did I say 0? Anyhow, so we have to assume that mu is different from 100, but it does not help our algebra because when it is different from 100, we have to define then what is that value. So when we say mu is different from 100, it could be 99, 110, or 200. It could be any number other than 100. So we have to know, to calculate the probability, we have to know the specific value we are talking about. We are calculating the probability of type 2 error 4. That's, for example, so in this case, for example, I'm going to assume that mu equals to 99. That means there is a brand whose drug contains 99 milligram instead of 100. So it's 1 milligram smaller than it has to contain, it has to have. So it is a problem. It is a problem. Now then the problem is type 2 error is that you cannot detect the 1 milligram difference. So a brand is cheating somehow, like making small sized drug, which could be dangerous, say. And now your job is to detect the difference, 1 milligram difference. If you fail to detect it, then that's type 2 error. So then let's calculate that probability when a drug contained 99 milligram on average. What is the probability that you cannot reject the null hypothesis? It happens when you don't reject the null hypothesis. So it happens when this happens. So you don't reject H0 if X bar, the sample mean, is in between the critical values. The critical values, and so critical values is always around your belief 100. So there is your belief 100, and you define a certain margin of error around the belief. So that's the critical value. And if the observed sample mean falls within the critical value acceptance region, then you don't reject H0. That's when you may have type 2 errors. So this is that probability. Probability of type 2 errors is probability that X bar lies between the critical values so that the null hypothesis is not rejected, given that the true mean is 99 milligrams. So it's not 100. Then how would you calculate this probability? You know the critical values. We already have we have critical values here, and then you can standardize X bar because you know the true mean. We assumed that the true mean is 99. So using this number, using this assumption, you may standardize X bar. So let's do that. So critical values given and standardize using 99. Subtract the mean which is 99, and divide by the standard error. Standard error is using the standard deviation and sample size. It's the same. So there is no difference in the standard error. And if you calculate these numbers, now you have numbers that's not totally new numbers. So you have to find this probability using the standard normal distribution table or Excel. We learned how to calculate probability between 2 points for a standard normal distribution. So go back to chapter 6 if you cannot remember. So simply speaking, you have to find the cumulative probability at 3.96 and then find cumulative probability at 0.04, then take their difference. The difference in their cumulative probabilities equals 48%. So that's the type 2 error probability. It's a lot. So there is only 1 milligram difference, and you are almost half of the time you cannot detect the difference given 100 sample. So and in this algebra, let me just review this algebra again. You have to use 99 for standardization. So the reason why we needed a specific number is because we need it for standardization. And when you calculate type 1 error, you used 100. And now you are using a number different from 100. It could be 99. It could be like, for example, 98. If you chose 98, the probability will be different. You are going to have a different probability. So type 2 error probability depends on which value you assume. And also, still I did not specify what you obtained, what's the sample mean. Sample mean is not required to calculate type 2 error probability. So that's also clear from the algebra. And graphically, what we are doing here is, so when the true value, H0 is true, excuse me, when the null hypothesis is true, the center is 100. And everything is defined based on this sampling null distribution. This is the null distribution, the sampling distribution when H0 is true. So it's centered around 100, say. And you choose critical values based on the null distribution, but actually it was not true. So H0 was not true, so the actual sampling distribution, X bar, would be distributed like this, a little bit distorted. So then the critical value is non-central. And you are going to reject this much. So you reject outside those critical values. But the problem here is still this area. This area is the probability that H0 is not rejected, even if H0 is wrong. So H0 is wrong. So your probability, your X bar will be distributed around this point, which is different from your belief. Still, there is some probability that the X bar is too close to the belief, even if the belief is not correct. That's the point. Okay, that's what we are doing, what we just calculated. And this probability, this area is not symmetric, so it's a little bit, the numbers are not commonly used numbers. So, but that's usual, typical. Now then, let's think about a different number. Suppose that the true value is actually 99.98. It is almost correct, but 0.02 milligram smaller than the standard. Then what is the type 2 error probability when the difference is 0.02 milligram? As you can expect, it will be very difficult to find the difference anyhow. So then how would you write the probability of type 2 errors in this case? What is the probability of type 2 error in this case? 3, 2, 1. So then you have to think about the definition of type 2 errors. Type 2 error is not rejecting H0, even if it's wrong. It's wrong, especially the probability that you don't reject H0 when mu is 99.98. That's the case we are considering. And you don't reject, so not rejecting the H0, the null hypothesis, is these two cases when X bar lies between critical values. And this probability is calculated under the assumption that mu is 99.98. So the answer is E. E is, if you can calculate this probability, that is type 2 error probability in this case. Okay, then the algebra is almost always the same. We have been doing the same algebra like in from chapter 6, so now you can do it easily, I believe. So, but also note that standardization uses the number we assumed as the mean. So we assume that the mean is 99.98. So you have to use that to calculate, to standardize the normal distribution. Then you get, and then you have these numbers, and using Excel you can find it's about 95%, which means almost always you cannot detect the difference. 95% you cannot detect the difference of 0.02 milligram. And makes sense because the difference is very small, and it just like if you measure it, it looks like 100 gram, it contains 100 milligram correctly. So you cannot reject the null hypothesis because the truth is so close to your belief. So compare the type 2 error probabilities depends on the value we consider, we assume, and obviously as the difference, deviation from the belief, it becomes smaller, the type 2 error probability will increase. You are more likely to fail to detect the difference as the difference is small. So, that's what I'm saying. H0 is deviated by 1, and now H0 is deviated by 0.02 milligram. So smaller difference is harder to detect, so you are more likely to miss it. That's the intuition behind it. Okay, so and then now let's compare type 1 and type 2 error probabilities at the same time. So remember, the key idea is type 1 error probability, type 1 error happens when you reject. Type 2 error happens when you don't reject, right? So in some sense, they are trade-offs. So when you increase rejections, when you reject more, you are going to increase the number of type 1 error, probability of type 1 errors. But type 2 error probability will be reduced because you are rejecting more. So type 2, there is lower chance of not rejecting H0, so lower chance of type 2 error. That's how it works. But still, however, type 2 error cannot be greater than 1 minus alpha. So remember, alpha was 5%. So you are going to reject 5%, top 5%, and you not reject 95%. So the 95% becomes the maximum of type 2 error probability. So if all of the non-rejections you make is an error, then the probability will be 95%, right? Because you are so like, let me put it again. So when you say significance level is 5%, you are rejecting top 5% and not rejecting 95%, bottom 95%. So then suppose that the bottom 90% you don't reject, and suppose that all of them are type 2 errors. All of them were actually had to be rejected. Even this worst case, the type 2 error probability is 95%, because that's the maximum you did not reject. So the maximum type 2 error probability is 95%. On the other hand, the rejected 5% is type 1 error probability. So it's a flip side of a coin. So the higher alpha is, you reject more, so it reduces type 2 errors, but it will increase type 1 error chances. So it's also the trade-off using balancing out the rejections and non-rejections. Okay, I'm going to stop this video here, and in the next video I will continue to another concept. Thank you for watching.